Thanks. Great to be here. So I'm going to tell you a little bit about my lab. And really what motivates me is trying to understand and restore animal behavior that's been lost. So, primates have an immense behavioral repertoire, whether it's a monkey picking fruit out of a tree, or whether it's the Canadian World Cup team trying desperately to not get knocked out of the group round. But eventually, these movements, complex as they are generated by similarly complex circuits in the brain. You have sensory, motor, and cognitive regions of the cortex, you have subcortical and brainstem nuclei, you have the spinal cord, and eventually these all create these movements. And the key is that these all must work together. And if they're not really providing the right concerted co-activations and the right interactions, then you get to lose a lot of function. And neurological diseases are a great example of this. I like to use the example of Parkinson's. It's of course a very complex disease, but one of the kind of key expressions is the death of these dopaminergic neurons in the basal ganglia. As a consequence, you get these very widespread motor and cognitive deficits in the behavior of these patients. So one of the goals of my lab is to try and really restore this type of movement that's been lost in these diseases by directly interfacing through neurotechnologies with these neural circuits. But because everything is connected, because these are really cohesive, holistic, broad circuits, I think there's really a lacking understanding of how these circuits interact. So if I were to say about my overarching aim is to build this kind of holistic, brain-wide view of how movement is generated. And I do this through three approaches, three axes. So I do experimental neurophysiology in monkeys, and I inform these experiments with theoretical models of the neural data that I record, and ultimately try to apply these to neuroprosthetics to restore lost movements. An example of what I've been working on most recently is spinal cord stimulation to cure Parkinson's and spinal cord injury. And I think of these three axes as really quite interacting and almost inseparable. And at the heart, linking all of this, is my work in artificial intelligence, which I've been pursuing through an appointment at MILA, the Quebec AI Institute. And through these different approaches, I can take a lot of different techniques that can be complementary and to kind of give you an example of how these things work together. So the research program I'm developing now, my core experimental work is a non-human primate platform where monkeys interact with this industrial robot to do very naturalistic yet experimentally controllable behavioral tasks. And then while they're doing this, I record as many neurons as I can from as many brain regions as technology will allow, and that's ever increasing as time goes on. And then I used computational modeling to actually dissect the interactions between all of these different regions that I record and try and extract principles that allow me to interface through neural decoding or reading information from the brain and encoding or writing information into the brain approaches. And once I have these decoders, I can apply them to, say, spinal stimulation to restore movement, and these informs the next rounds of behavioral experiments that I perform in these monkeys. So with that, that's kind of the overview of the types of things I do. I'd love to chat at the cocktail hour about any possible collaborative avenues between our work, and I'd like to thank the faculty for letting me speak today.